In this video, we're going to discuss another colligative property, that of osmotic pressure. Let's think of a simple U-tube here. Not the kind that plays videos, the kind made out of glass. And in the middle, there's a barrier. Now, this barrier can be made of lots of things, but for our purposes, this is what we call a semi-permeable membrane. This is a material that allows certain types of molecules through, but not others. In this case, water. So this is semi-permeable to water. Well, we can put some liquid in and it'll drift through and get to the other side, and eventually we'll have liquid on both sides. And so you have water molecules filling both sides of this tube. Now, if to one of the sides we were to add salt or sugar or something that isn't water, well, let's zoom in on what's happening right at the membrane. Water molecules are able to pass through, but not all the time. They're semi-permeable. Some hit and bounce off, others will bounce off as well, and some pass through. So at any given moment, there's so many impacts per second on that membrane. Some percentage of them succeed at passing through, but that's true for the other side. Some bounce off, some pass through. What this means is that there's a rate at which molecules can go from the left to the right, and a rate at which they go from the right to the left. Well, if it's pure water on both sides, then there's the same amount of water, the same number of impacts, the same percentage can get through, and these two will be the same. So for every 5 or 6 molecules that move to the right, you'll have just as many that move to the left. The net effect is there won't be any more or less on one side. But as soon as we have salt or sugar or something else in there, now some of those impacts are salt. Plenty of them are still water, and some of those waters will even pass through. But on the other side, they're all water. The net effect is that on the side with the solute, the material that is dissolved, less of the impacts per second are water. And so if only 10% of the water impacts or something can get through, well, there's just less of them. Those rates change. The side with the solute has a lower rate of water passing through to the opposite side. The net effect is that over a little bit of time, some of the water molecules on the pure water side drift over into the solute side and not as many come back. Over time, that's going to raise the water level on the solute side, and it's going to lower it on the pure water side. Well, if you ever just had a straw or a tube and you had liquid in it and you had both ends open, water tries to be at the same level. Gravity pulls down, it pushes back and forth, and they're supposed to line up. If they're ever not lined up, well, let's just think back to gas laws. You could have had a manometer, and you would have had some mercury. And then as you filled gas on this side, it would push down harder. This would lower and this would raise. And you get a difference in heights between the two. And you could use that to calculate out the pressure. Well, that can happen here. The difference in height between where our water on the pure side ends up and our water layer on the mixture side ends up, we can use to calculate out a pressure. This is literally where the pressure part of osmotic pressure comes from. It appears physically to be very much the same as just having a gas push that material up the tube. Osmotic pressure gets capital Pi symbol, and it is equal to the molarity of the solution, RT. Well, hey, pressure and molarities is moles over volume. This is really PV equals nRT. This really is just the modified version of the gas law equation. We're looking at the same kind of physical properties. We're looking at opposed forces due to interactions and collisions, and very much it works similarly in the calculation. So we can actually figure out how much pressure is being exerted in excess as the water tries to flow in to dilute the solution using this calculation. So let's do an experiment. Let's take a 0.001 molar just sugar solution. Let's use that and find out its osmotic pressure. And we'll say we're at standard states of 25 degrees Celsius. We're not concerned about the outside pressure. Our container's open on both of them, so outside gas is 1 atmosphere in both directions. The only thing affecting the rise in this tube is the osmotic pressure. And so our osmotic pressure is going to be equal to 0.001 molar. Let's go ahead and do this in torr. So 62.36 torr per liter, or torr liter per mole Kelvin, and 298.15 Kelvin. What we'll find is that our osmotic pressure is equal to 18.6 torr. What's that mean in terms of our height? Well, we can do a little conversions and figure out, hey, how much is it going to raise on one side? Let's do that. We can assume our tube is any volume, but let's just make it easy. Let's say it's got an area here of the column of 1 centimeter squared. And then any height we'll measure in centimeters. And so every centimeter we go up is going to give us 1 cubic centimeter, or 1 milliliter. So we can kind of find our volume making this assumption. If it was a wider base, we'd have more total volume, but because it would spread out over more base, the pressure is still going to be the same if we use the units of grams per centimeter squared. So we can do some conversion here. 18.6 torr, there's 760 torr, and every 1,033 grams per centimeter squared, which is 25.27 grams per centimeter squared. So we can convert it into a more metric-based to bring back and look at our tube volume here. And so I need some height where the total volume is going to weigh 25.27. Well, we're a pretty darn dilute water solution, so this is probably pretty close to just water, which is pretty close to 1 gram per milliliter at 25 degrees Celsius. So how many centimeters tall would I need to be if each centimeter gives me 1 milliliter and each milliliter is 1 gram? This tube would be about 25.27 centimeters tall. That is how much higher the water layer would be. Good part of a foot for a 0.001 molar solution, for a 1 millimolar solution. That's actually a good deal of osmotic pressure. It doesn't take very much stuff to start pushing things up onto the concentrated side of the tube. This has consequences in life, and this is why saltwater and freshwater organisms don't survive in the other environment. Your cell, or any creature's cell, has little semi-permeable membrane components where water can get in and out. So if you have a bunch of water on the outside and the inside, and say you are a freshwater creature in the ocean, washed down the river, well then your leave rate of water escaping is going to be much greater than the water getting back in, because plenty of times the salts will just bounce off. The net effect is that a freshwater organism will shrivel. It dehydrates. Literally floating in the ocean, it dehydrates and loses water content because the leave rate is much greater than the gain rate for water for that freshwater cell in a salt environment. Conversely, if you have a saltwater organism, which has plenty of salts inside, and you transport it to a freshwater system, well, that fresh water is going to enter far more often than water is going to escape. As a result, pretty quickly, that cell bloats as it starts filling with water and can rupture. This is actually part of what's so hard on things like salmon and other fish coming in and out through the estuaries. They spend a lot of time slowly adjusting their salt concentrations as they move from the ocean to the deep estuary to the closer estuary to the rivers and up to the fresh water. That's why a lot of organisms spend a good deal of time swimming around the sound and then slowly working their way up into the rivers. Making that adjustment, if you don't do it slowly, will literally cause the cells to either collapse or burst. So osmotic pressure isn't just a quick side note. It shows up as vital for life. Maintaining the proper balance of ion concentrations is vital for all of our neurons to fire and our cells to operate correctly. It's why chugging a gallon of water can be deadly. There's plenty of times in history where radio shows have had competitions and they had people see who could chug the most water the fastest, and somebody passes away from it. I don't know why radio stations still do this every few years. You think they'd have learned, but it does happen, and this is part of why. Your body needs certain ion concentrations to make processes work. If you disrupt it, things start moving where they're not supposed to, and it doesn't work properly. Here's the idea behind osmotic pressure.